Assalamualaikum warahmatullahi wabarakatuh, and hi to my students. Welcome to the next video lecture for the subtopic of rings. Previously, you learned already the basic definition of group such that it satisfies four properties. The first one is closed, associative, it has identity, and if it has identity, it can have inverse. For the abelian group, you add one more, which is commutative. Right now, it's a larger algebraic structure, larger than abelian group and even larger than the group, which is also known as ring. A ring is defined as R such that it has two binary operation, which is plus and also multiplication. It has specifically these two, only plus and also multiplication. You can define ring as any of the set. For example, if I take integer, but if you define a ring, it must be plus and also multiply. Ring can be defined as definitely a ring. Any set is a ring if it satisfies three basic conditions. The first one is that this given R is abelian under addition. The second one, the multiplication is associative. And the last one, it satisfies left distributive law. Okay, this is the new properties that we never mentioned in the previous lecture. Left distributive law, it means that A times B plus C is equivalent with A times B plus A times C. And it must also satisfy right distributive law. And the right distributive law is given like this: A plus B times C on the right, it will produce AC plus BC. Okay, three properties, three conditions that you must satisfy, plus one new property, left distributive law and right distributive law. Right now, let's try to do the Z first. Okay, for the previous question, let a ring defined as integer, set of integer, plus and multiply. If we want to prove it is a ring, it must satisfy three conditions. Let's start first by showing that indeed this addition of integer is abelian. Okay, the first condition of a ring, the addition is abelian group. So we divide this into three big proof here. You know already how to prove an abelian group. Okay, we start by the first one, for abelian group. For the set of integer, it must be closed under addition. For every for every integer, A plus B produce C. C is also an integer. Definitely, the Z plus is closed, as we discussed from the previous lecture. The second one, associative. Okay, the addition of integer is associative. For every A, B, C in integer, this happens. A plus B plus C is equivalent with A plus B plus C. It is associative. The identity also exists for the addition of integer. For every integer, a plus 0 equals to 0 plus a, you get back a. Identity exists, which is 0. And if we have identity, we check for the inverse, and the inverse for integer, a plus inverse equals to inverse plus a, you get back 0. The inverse for every a is minus a. We proceed this proof with the next commutative. For every element, for every two elements of integer, it is known a plus b equals to b plus a. Therefore, it is also commutative as well. Therefore, I managed to prove that the addition like this. The addition of integer is abelian. Then we satisfy the first condition for ring. You need to show this one first. The next one, the condition of ring, the multiplication is associative. Therefore, you need to think, is the multiplication of integer is associative? It's just a simple statement of properties there. I take for every 3 integers, it is known that a times b times c is equivalent with a times b, then u times c. Therefore, to conclude, the z under multiplication obviously is associative. Now the second condition of ring is satisfied. Let's move ahead by showing the left distributive and right distributive law. For the left one, a times b plus c, a b plus a times c. For this one, it's very tedious if you want to show for every possible 3 integers. It's just a statement there, and it is also wide known that the multiplication and addition of integer behaves this way. So let me start with the example first. This is not the proof, it's just an example. I take a equals to 1, b equals to 2, c equals to 3. How to visualize, to demonstrate this left distributive law? If I take these 3 integers 1, 2, 3 there, let us start with 1 times 2 plus 3. Okay, the left hand side first. This will be 1 times 5 will be 5. This is for the left hand side. For the right hand side, 1 times 2 plus 1 times 3. It happens to be 2 plus 3, which is also 5. This demonstration, this example shows that 1 times 2 plus 3 is equivalent with 1 times 2 plus 1 times 3. You can try any of the different 3 integers, it will satisfy left distributive law. It's enough for you to mention for every 3 integers from integer, it really shows that a times b plus c is equivalent with a times b plus a times c. We must have this general statement for every 3 integers. A times b plus c is equivalent with a times b plus a times c. That is for left distributive law. Symmetrically, for the right distributive law, the difference this time is that A plus B times C will be AC plus BC. And suppose I use the same three integers from the previous one. I show the left hand side first. 1 plus 2 times 3 is equivalent to 3 times 3 equals to 9. And how about the right hand side? 1 times 3 plus 2 times 3 is equivalent with 3 plus 6 is also 9. Therefore, 1 plus 2 times 3 is equivalent with 1 times 3 plus 2 times 3. This shows that for these three integers, 1, 2, 3, it satisfies right distributive law as well. Therefore, we must have a general statement to complete your proper proof. For every three integers, actually, A plus B times C will equivalent with AC plus BC. Therefore, ring of R for Z plus multiply satisfy both left and right distributive law, as it satisfies number 1, number 2, and also number 3. It's definitive that this ring is a ring because it satisfies three conditions. I repeat back the condition that the first one is that the addition is abelian, the multiplication is associative, and lastly it satisfies both left and right distributive law. Let's try another example. Let us use a smaller one, Zn, for the case of Zn. And let me make the scope smaller. Suppose it is a Z4. Okay, so let us test whether Z4 is a ring or not. In order to do for the case of Zn, Z star n, and also Un, it is better for you to develop a Cayley table first to make our explanation much better. 0, 1, 2, 3, 0, 1, 2, 3. This time it's because it involves two binary operation plus and multiply. Therefore, you need to have both of them. The first one is plus and multiply. Let us do both. 0, 1, 2, 3, 1, 2, 3, 0. For the multiply, three, 6, 4, 2, and 1. Okay, finished. Then actually you need to show that the addition of Z4 mode 4 is actually abelian. If you do the process of by proving a group, definitely I will not write the solution back. You can refer from the previous video lecture. Is that indeed Z4 plus, it is closed based on the properties of integer. It is integer addition, it is associative, it has identity which is 0, and the inverse for 0 is 0, inverse of 1 is 3, inverse of 2 is 2, and inverse of 3 is 1. And the addition is also commutative as well under Z4 because the addition of integer is commutative. Therefore, Z4 is indeed abelian. Okay, this time for the multiplication which happens in Z4, I want to investigate it, write it in the statement specifically. Is Z4 multiplication is associative? Let me start first by demonstrate to you this is not a normal multiplication. This is multiplication with the inclusion of mode 4. If I want to demonstrate, I take A equals to 1, B equals to 2, and C is equal to 3. 1 times 2 times 3 is 3. 2. Okay. Let's check whether it is associative. 1 times 2 times 3. Okay. 2 times 3 in this case is not 6. 2 times 3, please look on the Cayley table for the multiplication. 2 times 3 is 2. 1 times 2. 1 times 2 is 2. Oh, I skip it. Okay, 1 times 3, 2 times 3 is 2. 1 times 2 is 2. And if we do the front part first, 1 times 2 is 2. Then you times 3. 2 times 3 is 2. Based on this example, 1 times 2 times 3 is equivalent with 1 times 2 times 3. Definitely this is associative. You take any 3 integers in Z4, it will be associative. To sum up this section, you can answer it like this. Based on the properties of integer multiplication, Z4 multiplied is associative. You can leave your answer like this. You can also have an alternative conclusion. Some of my students did this. As multiplication is associative, then Z4 is also associative. I accept both of these examples, but you must write in a general term. If you just put this part example without the general statement, it will not be a good answer. Let's try to demonstrate for the left and right distributive law. Okay, for this case, whether it satisfies left and right distributive law. The third condition, we start with the left one first, such that A, B plus C should be equal if it is satisfied AB plus AC. And let's use this example as well to demonstrate whether it satisfies left distributive law. Okay, 1 times 2 plus 3. This time you need to look at both Cayley table because it involves plus and multiply. 2 plus 3, okay, let me make sure that you can see this clearly. Okay, plus multiply. 2 plus 3 here is 1. 1 times 1 is 1. And for AB, one times 2 from the multiplication Cayley table is 2 plus 3, and 2 plus 3 from the Cayley table of addition is 1. Therefore, 1, 2 plus 3 is equivalent 1, 2 plus 1, 3. It satisfies left distributive law. For the right one, I need to take it up. Okay. For the right one, such that A plus B times C should be equal to A times C plus BC. The same three integers 1, 2 and 3. I take 1 plus 2 times 3. 1 plus 2 here is 3 times 3. 3 times 3 is 1. And for AC, 1 times 3 plus 2 times 3. 1 times 3 is 3 plus 2 times 3 is 2. And 3 plus 2 is equivalent to 1. It happens to show that it satisfies right distributive law as well. Okay, again, this falls under the same principle. How can we test all of the integers whether it satisfies left and right distributive law? Again, for this case, it's sufficient for you to show just in the general statement like this. For every A, B, C, which is an integer, it behaves this, this is Z4. For every element in Z4, as the integer addition, I cannot say like that. Based on the properties of the integer, because it combines both addition integer and also multiplication integer. Based on properties of integer, for every 3 integers in Z4, it satisfies left and also right. Okay, as the addition of Z4 is abelian, as the multiplication of Z4 is associative, and we just managed to prove based on the property of integer, put in the general statement that for every 3 integers it satisfies left and right distributive law. Therefore, our main conclusion, if R is defined as Z4 plus and also multiply, is a ring as well. This concludes the section for ring, and let me proceed with the commutative ring. Commutative ring is basically a ring where the multiplication is commutative. It's very simple. From the previous ring, we need to check 3 conditions. For commutative ring, you just add up one more properties, which is that the multiplication of R is commutative. That's all. So it must be a ring, but with the addition of the properties is that the multiplication must be commutative as well. For the addition, it has been proven to be commutative under the condition, the first condition, which is the abelian. The addition must be abelian. Then it constitutes that it must be a ring. But for a commutative ring, you need to check for the multiplication whether it's a commutative or not. So for this first example, let's say the question just now, R is defined as Z plus and multiply, where we already show that this is actually a ring. For the multiplication part, where it is a commutative or not, we just can see that for every two integers, a times b is equal for b times a. That's all. Therefore, we can say that Z ring is also commutative ring. And same goes for the example when the ring is Z4. Based on the properties of integer, the multiplication which happens in Z4, a times b is also equivalent with b times a. Z4, the ring of Z4 is also commutative ring. Again, for this topic of abstract algebra, please master each of the properties that defines any of the algebraic structure, starting from the smallest one, semigroup, monoid, group, abelian group, ring. Right now is commutative ring. In the next video lecture, we will discuss the largest algebraic structure that you will learn. Until now, thank you and goodbye.